All right, so let's move on. So here we are going to consider data that have a binomial or that follows the binomial distribution. And that data are usually binary in nature. Binary in the sense that the outcome variable is either yes or no, infected or not infected, success or failure. So when your outcome of interest is in that nature, then we are talking of a binary data. And binary data, we assume that they follow the binomial distribution. So we want to consider the binomial model under the Bayesian framework, the binomial regression model under the Bayesian framework. Under the frequencies framework, we'll be talking of fitting the logistic regression model. So the logistic regression model is used to describe the binomial data. We are going to look at how we do that under the Bayesian paradigm. So we are saying that binomial and binary response data with one or more covariates can be analyzed through a basic generalized linear model with a specified link function. We use the logic link function to describe the binomial distribution. The logic link function. So here we say, let y, which is a vector, and the values of y to be y1, y2, up to yn, be n independent binomial or binary random variables with probability mass function. We are not talking of density function. We use density function when we are talking of a continuous data. And then we use the probability mass function when we are talking of a discrete data. And the binomial distribution for the data or the random variable y, given a set of parameters, theta, is m, which is the number of observations or trials, choose the response variable, and then, so the theta is the probability of success, and 1 minus theta is the probability of failure. And then we have our n minus our data values. And we are saying that y can take a value of 0, 1, up to mi. And we are saying that mi is greater than 1. So if we have our probability of success, which is theta, to have a function of, or to be a function of the covariate and the parameter, vector of parameter describing the covariate, then we can represent what we have inside the bracket here with eta, just like we saw yesterday. We represent that by eta, which is given by this. So in effect, we can write this as theta equals to f of eta. So this is just going to be a function of the eta, where eta is the linear combination of the parameter estimates. Now, we are saying that where f is a cumulative distribution function, and it's typically the log-link function. So the log-link function specification defines the data type that you are dealing with. So if you are dealing with a normal data, we use what we call the identity link function. If we are dealing with the Poisson data, we have the log link function. If we are dealing with the binary data or the binomial data, we use the logit or the probit link function. So the logit link function for the binomial distribution, so you can see that the parameter, which is the probability of success, is equals to this. So if we divide both sides by f, then we are going to have an inverse of f. And that is exactly what we are having here. So we have an inverse of f of, so this is supposed to be -1, f -1. Because if you divide, if you divide here by f and divide that, so this is going to be inverse of f of this function here. And that is equal to the logit. Remember your logistic regression model is the probability of success compared to the probability of failure, or the probability of the disease compared to the probability of not disease, probability of exposed to the disease, probability of not exposed to the disease. And that is equals to the linear combination of the parameters. So f of theta, we are saying that it is equals to phi of theta. F of theta is equals to phi of theta. And that yields the probit link function, where phi is the cumulative density function of the normal distribution with mean 0 and then variance 1. So this is the complementary log function, how it is done. Now we are looking for how to implement the binomial regression model under the Bayesian paradigm. So first, remember, under the Bayesian, we need to define our posterior distribution. And to define the posterior distribution, we need to know the likelihood function for the data, and then also the prior distribution for the parameters in the likelihood function. So in general, rewriting the binomial formula that we have here. Rewriting the formula that we have here. Theta is now in the form of the parameter estimates. Let's write it in that form. So our likelihood function for the binomial data, given the parameters, is going to be the product of the data distribution, which is mi, that is the number of observations you are going to choose y from. This is just m combination y, m choose y. And then our probability of success, the theta, is now this one here. Look at it. The probability of success, the theta, is now the eta. Yeah, the theta is now equals to the eta that we have here. So the theta, look at the theta. This is the theta. The theta, which is the probability of success, is equals to f of x and the beta. But we say that this x beta, which is the mean of the regression equation, is equals to this. So we can simply replace this by eta. So if we replace that by eta, what that means is that we are going to rewrite this equation. So wherever we see theta, the probability of success, we will substitute that by f of the eta here. So we move on here. So here we are going to have f of eta to the power y. And then here we are going to substitute the theta with f of eta. And then that. So what we are just simply changing here from this equation is that we are replacing the theta that we are having here by the f of the eta, because we said that theta is equal to this. But we know that what is inside here is also equals to eta. So just replace that. That is exactly what we have done. So from equation, from 7, I'm referring you back here, from 7 here. From 7, we know that theta is going to be equals to, remember your logistic regression. We can solve that. Okay, we can prove this. Theta, that is the probability of success, is equals to the linear combination of the parameters divided by 1 plus the linear combination of the parameters. Go back to number 7. When you come to number 7, look at it here. The log of this is equals to what we have here. Now, if we want to find theta, what do? Divide here by log and divide here by log. If you do that, you are going to have theta over 1 minus theta equals to exponent of x beta. So you make theta the subject. How do you make theta the subject? To make theta the subject, what that means is that you are going to multiply 1 minus theta by exponent of x beta. So you have theta to be equals to 1 minus theta multiplied by the exponent of x beta. So when you multiply by exponent of x beta, you expand the bracket. So theta is going to be equals to 1 multiplied by x beta minus theta multiplied by exponent of x beta. So when you do that, you group like terms. So you are going to have theta. Then because this is minus, you take it across the equal sign, it becomes positive. So you get theta plus theta times exponent of this. And then that will be equals to that. So I will make my theta the subject. And when you make the theta the subject and divide, this is what you are going to get. So this becomes the probability of the success. So look at how the probability of success is now affected by the risk factors. This is the probability of success. Remember, this is a probability. So there is no way this value will go beyond 1. This is the probability of success. Now, let's substitute that. We are saying that our theta is equal to this. So let's substitute this in place of our theta. Let's substitute the whole of this in place of theta. Theta is here. Let's substitute that in place of theta. If you substitute that in place of theta, this is what we are going to get. So wherever you see the theta or the eta, you substitute that. So we substitute our theta. So here we are going to substitute the theta here. So that this whole thing that you are seeing here is theta. So we substitute it here to the power yi. Then this place too, we substitute minus the whole of this here, and then all to the power that. So it's going to be 1 minus the whole of what we have here, all to the power m minus y. And that is what we have here. That is the likelihood function alone. That is the likelihood function alone. We haven't talked of the prior distribution and the posterior yet. So we are saying in 12 here, in 12 above, the unknown parameters are beta naught. We don't know beta naught. And then up to this is supposed to be beta P, the last one, up to the last beta. We don't know them. What the values are, we don't know them. That is what we are going to estimate. That is what we are going to estimate. So if we are going to estimate these parameters under the Bayesian framework, what that means is that we need to define the prior distribution for these parameters. One may prefer to provide prior information on the odds ratio, that is the exponent of the beta scale, and mathematically transform them back to the logit scale. So someone can deal with beta values, someone can just deal with just the exponent first. So the odds ratio is the exponent of the parameter estimates. So here we are assuming that, remember when I taught you guys environmental statistics under the regression model, we mentioned that the parameter estimates are fixed. That was what we said. That was what we said. The parameter estimates are fixed. And when you go back to those slides, I stated there that under Bayesian framework, the parameters are assumed to have a stochastic or to have a probability distribution. Today you are seeing it now. So here, our parameters are assumed not to be fixed anymore, but to have a particular distribution, and we are assuming a normal distribution for the parameter estimates, and the mean for this parameter is given by the mean J, and the variance for the parameter is given by sigma square J. So in general, if we know the mean of this parameter is this and the variance is this guy here, then we can write the prior distribution for this parameter as beta minus the mean divided by the standard deviation. We can write it as this. So what that means is that we need to define the distribution for the mean here and also define a distribution for the variance here, because we are assuming that they are not also fixed. Parameters are not fixed under Bayesian paradigm. So we supply them. So the most common choice of mean is 0. And the standard deviation is usually chosen to be large because we don't want to assume that we have too much information. So when your standard deviation is large, what you are simply saying is that you don't have much information. I'm asking you for information and you cannot give me much. That means your error or your deviation is going to be very large. And that is non-informative. So you can assume that the variance is non-informative, and therefore you assume a non-informative prior for that. And then the mean, you can say that it has a mean 0 and a given variance. So the common choice, you can choose your standard deviation to be 10 or to be 100. That is large enough to indicate that actually you don't have much information about the study you are undertaking. Then to get the posterior, so what that means is we will multiply the prior distribution for the parameters by the likelihood function to get our posterior. So the posterior distribution is going to be the posterior distribution of the parameters beta is a beta conditional on the covariate and the data is equals to the data likelihood multiplied by the prior distribution for the parameter estimates. So we multiply our density function by the prior distribution here. Now you can see this function, very complex, and whether we'll get a closed form, we don't know. So the best approach is to resort to numerical estimation, the use of numerical methods to estimate this. So in next semester, we shall see how we will simulate the parameter estimates from these models. The focus of next semester is how to simulate or to implement these models using a software. So we can use Winbacks to solve this. We can do this in Winbacks. We can do the analysis in R. We can do it in SAS. We can do it also in Stata. There are various softwares that you can implement these models. Any question? Any question?
Sir, please, we can't hear you.
The lecture is over. So what I'm asking you, is there any question that you would like to ask? You still cannot hear me?
No questions, sir.
Ben, any question? Hello?
Sir, no question.
Are you the only one there? Okay, if there is no question, we end our lecture here. So next week we meet for tutorials. So prepare your questions where you have problems, where you have difficulties in understanding. Prepare them and then we shall come and then address them. So next week, our first online meeting is going to be tutorials. So where you raise questions, issues that you have, challenges that you are facing, and we will address them. If you are okay, then you come, then we spend some few minutes and then we go. If you have series of questions, then we spend the whole time discussing them. So since there is no question, I'll end my lecture here. I'll share the lecture slides with you via YouTube, so you will be able to listen to them. Okay, bye-bye.